All right, we'll get started. So last Tuesday, we were talking about the Byzantine case, and what we found was that we needed 3f plus 1. So in other words, f is the number of failing nodes. So we need 3 times that plus 1 in order to be able to successfully protect against the Byzantine nodes. So just take 2 minutes and try and explain it to each other so that you refresh that in your memory. All right, so what did you come up with? Why do we need 3f plus 1?
So the overlap of 2 forms always has a good note.
Right, go back to quorum. Quorum is where we always go in all of these consensus protocols. How do we know that we have agreement? And we always have agreement because we have overlapping quorum requirements. We can't achieve that overlapping quorum requirement with only 3f nodes, because that means that we could actually have a quorum that's only traders, only Byzantine nodes. I mean, the interesting question to me is, could you organize this in such a way that you might end up with a better limit, a better number? And I'm not entirely sure it's impossible, but that's why most of the actual Byzantine work in the world is research and not production grade. So that's more of a question that you might be asking if you were in the research space, or if you were in the very tippy top end of production grade. I mean, if you're working at Google or Microsoft or Amazon, you might seriously be asking that question. How do we protect ourselves against multiple failure sources? Networks lie all the time. Disk drives lie. I think I mentioned that example before. And that brings me back to, of course, one of the fundamentals here in the course, which is we look at the failures. We say, how can things fail? How can we reason about the system in the face of such failures so that we can overcome it, so that we can actually fix things when the plane's wings fall off. That's why you're pretty super glue, right? But today we're going to go in a little different direction. Today what we're going to do is we've been talking about all these different ways of things failing. We've talked about limitations. We've talked about impossibility. Are they different, or is there maybe some sort of larger level scope that we can look at and say, hey, wait a minute. These are different manifestations of the same fundamental observation, the same fundamental property. So the four things that I'm going to be weaving together are the FLP finding, which was you can't have consensus with an arbitrarily delayed network with a single node crash. There's nothing you can do. You can't detect. You literally cannot detect any node's failure from an arbitrary network delay in an unbounded lifetime network. So in other words, if we can always delay that message one more step and make that take a little bit longer for us to say, oh, this didn't converge or this is broken, or it did converge and it's not broken, we can't solve that general problem. The way that we're fixing that in the real world is we're just simply bounding it. That model doesn't work, it's too general, so what we're going to do is we're going to change the model slightly. And that's a common technique, is you say, here's the thing I'm not going to be able to handle. That's why failure first is a good way of thinking about this, is that you're literally bounding the failures that you are willing to tolerate. The example I've used before is, have any of you ever seen Marvin the Martian in Warner Brothers cartoons, where so Marvin is a Martian who wants to see Venus and the Earth is obscuring it, and Bugs Bunny, of course, has to thwart Marvin's attempts to blow up the Earth. And my observation about that is always that you cannot protect against that particular category of failure. Or can you? Well, if we put our data center on Mars, we might be able to make it recoverable, but because Marvin couldn't be blowing up Mars, he would be blowing up Earth. But the point is that there's always a class of failures that you're going to look at and you're going to say, I'm not worried about that because it's possible, but it's not something that I can resolve. If the sun blows up right now, we'll all know about it in 8 minutes. But I'm not going to plan a data center. I'm not going to plan anything in my world for that particular eventuality because it's not likely. So even though, I mean, when you first start programming, mostly what you focus on is just trying to get the common case working. You know, oh my gosh, just get that common case working and ignore all the errors. And as you begin to mature in that process, you say, well, what kinds of things could go wrong that I can handle? You know, users put the wrong inputs in the fields, so I can check the fields. Okay, that's great. But then I start using the network, and the network can be flaky. So what do? Do I just simply give up when the network doesn't allow me to connect instantaneously? Probably on the version 0.1. You're just trying to get the basic logic working. But then you say, okay, well, but sometimes the network connection goes down, so why don't I just reconnect? Okay, so now I've handled a particular class of failure. We're in a domain now where we're handling difficult classes of failure, things that can go wrong that we need to really be able to reason about. And it only gets harder from here. But just because we say we're not going to handle that failure doesn't mean a year from now somebody's going to say, now you need to figure out how to handle that failure. How can you improve the system? How can you reason about that? So the failures will keep moving and evolving as you continue to work in the field. The whole field is continuing to move and evolve. How many of you think that AI is just going to go away? Is that a wish or a hope?
Well, it's going to go away. I just think it's not going to, at least not in the next 10 years, going to change a lot. It's not all it's
I don't know. I mean, I know that in software engineering, one of the things that's already happening is the use of AI for doing routine tasks is creating a situation that is breaking existing software engineering practice. So for example, pull requests. The classic example was that even without AI, the human ability to handle pull request traffic was being stretched. That most people would look at pull requests and they would spend a minimal amount of time looking at it and then say, okay, it looks fine to me. It passed the test, I did some basic review of it, I'm going to approve this PR. And the way that we primarily prevented failures from creeping in was through our testing infrastructure, through our continuous integration networking mechanisms. But now the pull request volume is so high that literally you can get 100 pull requests a day, and there's just no longer enough cycles for people to look at them. So they're automating it. I actually submitted a PR to Google for Gemini CLI. There's a bug that I discovered in some of the work I've been doing, and it literally means that there's a whole system of remembering things when they garbage collect the memory in the tool itself. They have a whole system remembering things, and they just weren't remembering it because literally there was nothing in the schema that said preserve this. And that means that you end up with a certain kind of decay. Literally, you're using Gemini, and that it goes through and cleans its memory space, and things that were important just get lost, and so then it starts to drift. So I created a PR, and the PR is actually automatically scanned by an AI bot, and it was classified by an AI bot, and it's now sitting in a queue that's waiting for a real human to actually go and look at it, even though the fix is there, it passes all the tests, it identified a potential, it was a very interesting theoretical security issue that I corrected fairly quickly. It's just like add another guard around it, and it sits there. And there's 600 PRs in this one repo. And that's why I don't think that AI is going to go away, because at least in software engineering, it is changing the practice. But on the flip side, what it means is that a lot of what you do in software engineering is going to shift, because it's going to use these tools to take care of more and more of the things that were time-consuming but not particularly interesting. I mean, nobody likes doing PRs. I have a hard time reading someone else's code and trying to figure out all the things it's going to do wrong. But I mean, I can do it. And we see that because Anthropic released Cloud Security, which they've been actively using on open source projects to identify security holes. That doesn't mean there's not going to be a job for you, because on the flip side, what's actually happening is it's increasing the demand for software engineers. They need software engineers. They need people who can walk in and solve problems. And that's exactly what we talk about in this class, over and over again. How do things fail? How do you work through those things? So we have FLP, we talked about that. We talked about the CAP theorem, which was first proposed uniformly in 2000 and more formally in 2012, which says you cannot have consistency, availability, and partition tolerance all at the same time. Now, partition tolerance is just going to happen. It's not something you can really say, I just don't work in that particular case. You'll have to deal with it. So it's mostly about consistency versus availability. And that's why we talked about different models of consistency, right? So we had everything from linear consistency all the way to eventual consistency. The two generals problem, which we just got done talking about, and the Byzantine bound that, I think that was Elizabeth. Was that Lamport? That was Lamport, I think. identified. Two generals was definitely a lot for it. What do these things have in common? They're all adversarial models. They're all something's going wrong. So they all relate back to failures. So in FLP, what we saw was the problem is network delay. So we have a proposer who completes phase 1. So he's got quorum. And he now sends his accept message. But of course, the network, for whatever reason, delays it. Maybe the packet gets lost. Happens. Those are networks. Presumably in 317, they don't tell you that networks are reliable, right? We build reliable, more or less, networks on top of unreliable networks, but we still don't guarantee real-time delivery. We'll get the packet there eventually. Did they make you read, what's it, RFC 1049? That's my favorite. It's IP over obviating carrier. They literally had a protocol for taking messages and strapping them to the legs of carrier pigeons. And it was an April Fool's Day RFC that has a tradition because they've actually added additional RFCs on top of it. So there's a quality of service over IP over obviating carrier. But that's kind of the point, is that literally when you start talking about networks, networks have arbitrary delay, and we'll get the packet there eventually. But here's the reason that this was a problem when we were building Paxos, which is the prepare from a different proposer comes in first, and so now the quorum, because this is a higher ballot number, the quorum now shifts to the new proposer. So A's accept now arrives late, but we've already seen a higher ballot number, so we can't accept that anymore because that's the race condition. That's exactly what it exposes. And if we just keep repeating that, we just, well, now proposer B's packet gets lost, and proposer C or A, doesn't matter, gets forwarded, gets a quorum, we never quite converge. So the really interesting observation here is that we're not lying here, we're just simply delaying a packet. So it's not quite the Byzantine case. It's the network is just unreliable. In the CAP theorem, the interesting instance there, which is availability versus consistency, is the classic, you walk to the bank machine to take money out. Your bank has 2 data centers. You walk into the data center in Oregon. And you have a balance of $500. You want to withdraw $400. Do you allow the withdrawal, even though someone in Virginia, there's a lot of Virginia and Oregon, but that's okay, might also be withdrawing $400 from the same account? Why is it a problem? Because the link went up. Two different data centers aren't talking to each other. So what you have here now is if you refuse, you have consistency. If you allow, you have availability, but you violate consistency. So this is a really clear example of the kind of trade-off we're talking about here. Now, when you only have 2 data centers, the only way you get quorum is if they both agree. That's why the minimum quorum size is effectively 3 nodes. And there's no benefit to a 4th node because you still need 3 nodes. Let's see, 4 nodes, you can't do it with 2, you have to do 3. So you go to 5 nodes, and you can do it with 3, so you can actually tolerate 2 failures instead of 1 failure. Okay, fine. That's why when these systems get built, that's why you'll notice that they normally, until they get really large, they normally just have an odd number of participants. In CAP, we know that we have to deal with partition partition events. Somebody unplugs a network cable, someone runs a backhoe through a piece of fiber optic cable in some place in the middle of wherever. A Russian trawler accidentally, deliberately drags its anchor across the transoceanic cable. None of these things have ever happened, of course. So what you lose is consistency and availability, because you can only have one of them during a partition event. But when the partition heals, you can get them back. So the impossibility here is only while the partition is ongoing, not when the partition, when we don't have a partition. So now this becomes a set of engineering trade-offs. There's not an absolute limit here. I mean, if there's absolute limits, they're easy because they're like guardrails I can't go over. I can't go faster than the speed of light. Well, actually, I can't go the speed of light is actually what the equation says. Which is why we end up with tachyons, because those particles go faster. But there's a singularity at the speed of light. That's why the physicists tell you the speed of light you can't get to. The two generals problem was the unreliable messenger issue. In this particular case, what we concluded was there was no way we could send a finite number of messages and come up with a robust conclusion. Think of it as the network keeps getting delayed, and therefore I don't actually know what the state of the system is. In physics, there's this concept of what's called the Heisenberg uncertainty principle. Has anybody ever heard of that? Do you know how you measure how fast something is going? Like with a radar or a laser? You bounce something off of it. You literally shoot something at it, you bounce something off of it, and you measure the bounce. And that tells you where it was and how fast it was going. But the very process of bouncing something off of it changes it. It's a fundamental principle of physics, is that you actually change the thing that you just observed. Okay. And the same thing tends to happen here as well. In Byzantine, we said, look, if we have 3 nodes and one of them is Byzantine, we're never going to be able to solve that problem. We don't quite have enough information. So if we allow up to F nodes to be Byzantine, we cannot ever have agreement with less than 3F plus 1 nodes. We need at least 3F plus 1 nodes to have agreement. That plus 1 is exactly what you said, which was it's the quorum intersection. We need that one extra honest node, and then we can actually reason about it. So here's the question to ask yourself now. I'll give you 3 minutes. What is the something that each of these results identifies as the source of the problem? What's causing the issue in FLP and in CAP and the Byzantine generals problem and the last one, which was right, the multi-node Byzantine consensus issue. So we'll do that. 3 minutes.
Yeah, I wasn't sure if that. Calm down. It's like a train. Just train up to. Because like you're saying the system, you're saying that. And you have to. Which one's the side?
All right. So what did you come up with? Did you see anything that fits between these? Or were you just checking your Bitcoin holdings now that Bitcoin's back over 70,000? You're rich. So you have any Bitcoin?
I shorted it.
You shorted it. So what I'll suggest is the common structure is that they all point to something that is unachievable if we assume some property of the environment. F Byzantine nodes, an arbitrarily delaying network, partitionability. All of these things lead to something similar. And what's nice about that is if you think about it, then you can say, okay, I can see how these start to relate to each other. So in each of these, we have a different degree of freedom. So in FLP, we have asynchrony. We literally have the fact that we can't tell you when the messages are going to arrive. In CAP, we have partitions. We don't know when the network's going to get partitioned or how long it's going to last. We have two generals, which is we have an unreliable communications channel. Now our network is flaky. And in the Byzantine case, we have traders. And we have ethno mode. And so in each of these, the actual way that we escape, so this is what we lose in each of those. We lose liveness in FLP, we lose consistency and availability in CAP. Now that's the combination of them, not either or, it's both. We lose certain agreement in the two generals case, and we lose agreement across the spectrum in the Byzantine case. So for our escape, what we do is we change the model. We change something, we say we need to assume one extra property now in order for us to be able to make this solvable. So we're not solving the general problem, we're solving a subset of the general problem. We're constraining the problem a little bit. Doing exactly what I said earlier, which is, I'm not going to solve this problem. I'm going to put this restriction on it. Is this the only way to escape these things? And I'm going to suggest it's not. It just happens to be the one that we ended up using to escape that. So when you're sitting there and you have to design a new system, you can use this as a framework or a way of thinking about the problem that says, what could I require that's different? Because that's going to give me a system that works, but works with a different additional constraint. There's this very interesting finding in mathematics from the 1920s. See, in the early 20th century, mathematicians decided that they wanted to actually prove a formal system of mathematics that was completely consistent. It started from base axioms and then grew from that those axioms into a proof of a rigorous, logic-based system that could answer any and every question. And this German mathematician named Gödel actually came up with a way of taking any such system that they could construct that was axiomatic, and it required that everything either be true or false. He could always construct a question that could not be answered within that system. Now, he did that in a very general way. It's actually the same basic technique that FLP used. It's the same technique that Turing used when he proved that there is at least one problem that cannot be answered by a Turing machine, and that is, given an arbitrary piece of code, does this program halt? Because literally the only way to answer that question was to run the program. And in that case, the only answer you could ever get back is yes. In the no case, it just wouldn't stop. So you could never come up with a no answer. But that's not a very satisfying thing here. Just keep running this infinitely long, and then you'll be able to tell me, well, when does infinity happen? When do we actually get to the infinite step? You never do. It's exactly the same thing that FLP has to deal with, which is you just keep pushing that final packet down out in time a little bit more. Just one more, just one more, just one more. And there's always a construction that says if I have a case here where we do finally reach that terminal point where we have to make a decision, I just push that message a little bit further out. And I just push that one a little further out and a little further out. And now you have the reason that it's not possible in FLP. It's not possible for you to keep that system alive. In CAP, it said, you can't get the latest value if you can't talk to the other partition. In the two generals, you can't tell if the other general has your message because the network itself is eating the message. And they keep sending couriers out and they keep getting shot. It happens. In the Byzantine consensus case, you can't verify this node is honest if you have f-lying nodes unless you have 3f plus 1. So the issue in each of these is I can't verify that in all instances I'll be able to do this. But that doesn't mean there aren't a lot of instances where I will be able to. So when I add an extra constraint, what I'm in essence saying is with this one extra piece of information, I can actually reason about the system and know that I can actually make the system work. But that one extra constraint means it's just a strict subset of your larger problem space. That's fine. That's why I said, when you are sitting there and asked to do something, you can take one of the classic examples, you can pull it off the shelf and you can say, great, this will solve your problem. But then you might step back and say, wait a minute, this doesn't really fit here. And if I had this other constraint, it would change the problem as well and still be bounded. It would still allow me to know that I can handle all of the failures within that domain. The first time I designed a transactional log system, I spoke with somebody who had built a transactional log system for a completely different project. His was for a general purpose database, mine was for a very specific use case, which was recoverability in a local file system. And he told me what the hard problems were, and I said, oh, well, I don't have to deal with that. I can just do this. I don't have to deal with that. I can just do this. I don't have to deal with that. I can just do this. Oh, and I can actually do something that didn't even have a label at the time. I found out that somebody, 15 years later, said, oh, gee, we can do this steal thing, is what they called it. It's exactly what I did. So the system ended up being very efficient because I was able to limit it in ways that applied to the particular usage case. And it was a good enough system that it's still in production use today. 35 years later. I mean, how much of your code do you think will actually still be in use 35 years from now? I hope a lot of it is. That means you're writing good code. It's got good generality. Code actually lives a lot longer than you think. Most of the code that enterprises still use, scarily enough, was written by people who are dead. Ever heard of COBOL? A miserable language. It literally was built for punch cards. Does anybody know how many characters you could get wide on a punch card? 8. And we still live with that limitation in modern systems. And the reason that we also see 72 is because when you put your punch cards together, the first 8 characters were used as a sequence number. So they would put a sequence number in there so in case you dropped your punch cards, you could put them back in order. It was kind of annoying when you had a big punch card block and you dropped it. And if it didn't have numbering on it, you wouldn't be able to put it back together. Essentially be like a jigsaw puzzle made out of microscopic pieces of puzzle. So small you can't really sort it out. How many of you have ever actually even seen a punch card? I mean, punch cards are ancient. The only time I used punch cards was in grade school and used them for an art project. But despite the fact that no one really uses punch cards anymore, it's still present in software. And COBOL was based on 8 cards, punch cards, screens, the whole 9 yards. And that code is still in use today. So your code might actually last a lot longer than you think it will. All right, so if every impossibility result is really about verification, then what should every escape have in common? 2 minutes. Here we go. So while you were off talking, I was asking Gemini what the optimal context window size was for a given large language model based upon the architecture of the transformer. These are the kinds of, dull, boring questions I ask while you're looking at the fun stuff. So, what'd you come up with? we just constrain the problem. We remove one of the degrees of freedom. Now, what we've been doing in each of these cases is exactly that. Oh, you've got F failing nodes. Well, you just simply need to have 3F plus 1 nodes. So you have 2F plus 1 honest nodes. And that's kind of the point. So in FLP, what we do in the real world is we just simply say, hey, look, it can only, that packet can only live for so long, and then it expires. Then we don't have the problem anymore. We've eliminated unbounded asynchrony and made it partially synchronous. We just put time bound in there. In CAP, we allow a stale read during a network partition, or we disallow mutations of the database in a partition. And those are both things that people routinely do in real practice. In the two generals problem, you just need to have a reliable subchannel. Handle it, right? It's like, well, that's, of course, it's really easy. We'll just simply build a TCP connection, and we know it will work. Except, of course, all the carrier pigeons are dead. So sometimes you might end up with a system where you say, oh, well, we'll just put this constraint on it, and then somebody else comes along and goes, well, that's not a very realistic constraint, is it? So in terms of the actual efficacy of your system, you might, just saying, you might actually want to keep the constraint that you add at least plausible. How many of you are building a distributed key value store as your capstone project? I mean, it's kind of a cop-out answer, right? It's like, well, okay, we can build this thing, it'll be kind of easy. And maybe you actually decide you're going to do it. It's not an easy project, honestly, the last lab, the sharded distributed key value store. But it's very interesting. The whole space of sharding. Why do we use key value stores? Modern databases are all built on top of key value stores. Why? What is the benefit of using a CRUD interface? What is a CRUD interface? Create, read, update, delete. Why? What's the constraint that we're imposing? Sorry? So he's looking at a performance as being a constraint. I don't think of that as the important reason for using a key value store. I have to think about that. Why would performance bounds be a constraint? I'm not convinced, but you can convince me.
What does constraint mean in this case?
It means a limitation or a restriction. I mean, if you want, we can put handcuffs on you too. That's a constraint as well.
No.
But that's a limitation or restriction of your arms.
Really, I guess one constraint is that if one of the pairs go down, as the user
I'm just talking about it. Why do we use key value stores? That was the question. What is the constraint on a key value store? And that's kind of interesting because it's a pretty simple constraint and nobody seems to actually identify it. You're going to make me actually give this one away, aren't you? It's atomic. Every one of those four operations is atomic. And that makes it really easy to reason about. When you create a key, you'll never get a duplicate key. You'll either get a successful create or you'll get a key collision. When you read, you will get a value. You won't get half of a value, you'll get a value. And you will know that value is one that you could have received Well, it was valid at some time you could have received it between the time you asked for it and the time you received it. That's the whole consistency guarantee there. I mean, I might have done a read, and then a moment later he did an update. And by the time I get the read back, his update has now been applied, so I'm not seeing the current state of the database. But at the time, I saw what the database value was, so therefore it was an acceptable or allowed value. Same thing with delete. The delete has either happened or it hasn't happened. So if I try to read the key, and you're trying to delete the key, I will either get a value or I get a key not found error. The reason that we use key value storage is they are absurdly simple to reason about, and yet that interface is sufficient for us to build a database on top of. And modern databases are all built around some variant of key value storage. And key value storage, as a result, have also scaled up really well. That's another nice property about key value storage. We can make them really fast. The fastest databases you can build are sitting on top of distributed key value stores. Today, if you want to have a high scale-up distributed database, what you do is you build a distributed key value store that uses the network card and talks directly to the memory in the computer. It doesn't even go through the CPU anymore. So they use NICs with essentially little processors in them that takes and update the key value store on the local machine. And this scales really, really well. They can do hundreds of millions of updates a second. And that's enough for pretty much anything you can possibly do at the moment. And when we run out of, when we need that extra capacity, the computers will run faster because computers continue to get faster. And key value stores, because they can be sharded, vertically scale really well. What does sharding mean? Let's take a window and shard it. What have we done?
Partition.
We split it up into pieces, exactly. So the reason that we do that with a key value store is because we can literally create a distribution across different nodes based upon the key. Just simply take the number of bits, for instance. So, if I have two shards, and then I just use a lower order bit or the higher order bit or a bit in the middle, it doesn't matter. You just choose an algorithm for doing that. If I put 3 of these in, then I just simply have to choose the routing of the keys. And generally it's done on bit masks because bit masks are super easy to compute and it can be done in a really stupid device at the front of the network, so it's very fast. And I can keep doing this. And then people get more sophisticated and they say, well, okay, but the problem with that is, what am I doing? I'm creating n points of failure. Because now I have n databases, n key value stores, that on top look like one big key value store, but underneath are smaller key value stores with disjoint namespaces. So, hey, do we have a way of building replicated key value stores? And what would it be? So he's going to do his with 2PC. Anybody else want to build one? I mean, it works. That's not the wrong answer. Anybody think any other way of building a replicated key value store? My God, it's been 4 lectures talking about it. Nobody can come up with Paxos. Damn. It's probably time to just hang it up and let you guys go back about your polymarket business. That's what I should be taking a bets on. I'll start putting bets on polymarket about who can actually answer these questions in class. And suddenly people will be motivated because we'll be able to get Bitcoin. What do you think about that? Cookies are probably cheaper. Right. So in fact, we use Paxos for doing things that are replicas because it is efficient. Or we use Raft, or we use Crack, or chain replication, or any of those techniques. Those all work at creating a replicated copy of the database. So the last lab in the DS Lab series is literally where you use 2PC on top to shard the database reliably. But underneath, it is a series of replicated Paxos nodes. So you combine different techniques to create this kind of distributed database. There's a database that came out of Berkeley, I think, a number of years ago. That when I first saw it, it was really cool because it was actually this key value store where you could run it locally, or you could start putting it on different machines and run it across the network, and it was scalable, very, very scalable, called Anna. And their whole point was that it's exactly the same interface, but it was an eventually consistent key value store. It wasn't a strongly consistent key value store. So if I give you a key value store, whether it's on a single machine or it's on an array of machines, it's the same interface on the top. You don't actually have to worry about it. This is the beauty of that underlying interface. So if I give you a key value store and I say this is a strict, strong consistency key value store, you can go build your database on top of it, and your database now, for free, gets distributed processing. So it becomes scalable. Now we can still build replication and whatnot in our distributed database on top as well, because we're going to build things like two-phase commit into databases. You can't use Paxos for non-replication. Paxos is about replicating the decision. 2PC is about coordinating different decisions across domains. So they solve different problems. And that's why you end up building systems that combine these things together. So we're restricting some degree of freedom. That was the point I was making here. In Byzantine, we can actually use signatures. So, in other words, the liars can't actually forge the messages of honest nodes. That would be an example of that. I don't think that's the one we used, though. The reason we're using that now is because that's actually the Bitcoin, the blockchain solution. All right, so they all work the same way. If you add something that is external that allows you to escape the impossibility. In FLP, we use randomization as a way of getting non-determinism. In CAP, we build things like external merge logic, which is what CRDTs actually do, or most commonly, the simplest thing to do is to simply say, hey, it's a race condition, the last rider wins. Easy enough. In two generals, then what we do is we just use replication. We just send lots of the same message over many different channels and hope that one or more of them get through. Now don't try to combine that with the Byzantine case where some of the messengers aren't reliable and actually substitute lies in there. Then you'll find out that some problems just can't easily be solved. In the Byzantine case, you can actually use something like a cryptographic signature, digital signature. Why do you sign code? You sign code because, in fact, it verifies that you are the person that you say you are. Open source projects now routinely require that people sign an agreement that says that you're giving up your rights to anything that you produce and contribute to the code base. Otherwise, they end up with this nightmare of copyright and so on and so forth. So they want signatures because that's a verifiable evidence that at some point you added that key to your personal account. So there's a way of tying it back to you. So the pattern here is we have an impossibility where some degrees of freedom block some particular property that we want, and we either restrict the freedom or we add an external source of information or behavior that allows us to escape the impossibility, and now we can get our property that we wanted back. Very general now. Right? We've moved from very specific examples of this and said, but we're really doing the same thing over and over again, repetitively, redundantly. But this is the point that I was making before. When I started talking about flexible paxos, the observation was there's more than one way to break the impossibility. There's more than one way to deal with the problem. So what Heidi Howard came back and said was, look, we just simply have to make sure that there is an overlap between these two different quora. We don't need to have the same set of acceptors in both of those quorums. We can use different acceptors. We can bounce it back and forth as long as there is always an intersection between the two. Now, the most trivial intersection is when it's the same group of people deciding. In both cases, then it's the same form. I just don't have to worry about it. But she said, wait a minute. So everybody just kind of assumed, it just had to be the same acceptors in both groups. And Heidi came back and she said, but that's not actually what Paxos said. It's not what Lamport taught us. That's what everybody interpreted Lamport as teaching us. What Lamport taught us was we just simply need this intersection property across the levels. And so she came up with a different solution to it. They don't have to have the same size. They don't have to have the same exact membership. So this is an escape. In this particular case, we escaped by restricting an assumption here. And what she did is actually very clever. She didn't break the Paxos protocol. What she said was, this was always allowed, nobody bothered to notice it. And the reason I mention this is because it does free up your options in the design space, and you at some point in your career will face circumstances, hopefully, because these are the fun problems to solve, you will face circumstances where you will run into something like this, and you say, wait a minute, what could I restrict here that would allow me to solve this problem differently than other people have solved it, and it would be better for my particular situation? In Spanner, Google implemented what they called effectively consistent and available by building a very tightly constrained network. What they said was, we get to control our own network. So, and partitions are very rare, but we're going to add this thing called true time, which is literally highly accurate clocks with a bounded uncertainty on the time. And then this is the clever part of it. All we'll do is just simply wait to tell people about the commits until it's outside of the window, the time variation window. And they did all the math, and they proved that in fact that meant that they had both consistency and availability. Why did you increase the time window? Because it would detect the collisions. The collisions will happen in that time frame, in that window. And you can then reason about it. But the trade-off there was, it means that it slowed their transactions down by as much as 7 milliseconds. I think that was a bound limit of 7 milliseconds. So Spanner doesn't actually violate CAP. What it does is it adds an additional restriction so that we almost never actually see that trade-off. So you just make it extraordinarily rare. It's not quite the same as saying it never happens. It's just simply saying it's not realistically going to happen. It's the same problem, same solution we used with QGenerals, which was just send more messages. Send 10 messengers out. What's the probability that 10 messengers are not going to make it through? And we'll talk about Spanner again, because it's a really interesting system. So we'll do a quick check here to see if any of this is sinking in, or if you guys are already thinking about lunch. So Spanner uses true time to bound clock uncertainty. Is true time restricting the freedom or adding something external? 2 minutes.
part of the system? Is it part of the algorithm, or is it something you added after the algorithm reduction? And you have it no, it's just I think it's the message that you said. It is something you started, but it's a part of the original
All right. What'd you come up with? Is it a restriction of freedom or adding something external? Or both?
I feel like it's both.
Okay, so what's the restriction of freedom?
The restriction of freedom. Like, because how I think the problem is like, how was true time introduced? Like, was it part of the original plan? Because if it is, then you're restricting the freedom. Or is it like something they realized, like after the initial version of Spanner came out, they realized there's like a huge problem, so then they added something external.
They actually built Spanner specifically to solve the problem.
So,
So I would argue it's both, because so the restriction of freedom is you can't actually send the response for the jitter time, basically the window when you might hear from someone else that they've already done what you're trying to do. The externality is the GPS clock requirement. All right, so let's, yeah.
so like for Spanner, like I think you previously said like the jitter is artificial. Right?
The jitter is actually a function of the variance in GPS clocks. It's actually computed based upon how accurate the clock is. When you look at the NTP protocol, the network time protocol, which all the computers in here are running to keep the clocks pretty close, usually the jitter is around 10 milliseconds. It's surprisingly good, and given that Dave Mills, I don't remember who he was, Dave Mills did that work in the 1980s. It hasn't really been replaced. There's an XKCD about NTP, where they have the picture of the modern internet, and then there's this one little tiny piece, it's like a Jenga kind of puzzle. There's this one little tiny piece on the right-hand side where it says, one guy in Nebraska has been supporting this. That was NTP. It wasn't like, he was literally, the guy who draws XKCDs was literally pointing to the fact that the entire internet was relying on this one guy who did it of his own volition. He wasn't getting paid to do that. And that the entire infrastructure would break when that fell down. And that kind of thing keeps happening over and over again, but that's a different issue. I'm not going to do this particular thing because we're going to run out of time because I talk too much. So, no replicated database can provide both strong consistency and sub-millisecond latency at global scale. Is this an impossibility result with the same structure? What's the freedom, what's the lost property, and what are the possible escapes? We're not going to do the whole thing there. But I will ask, does this look like an impossibility result? argue that it is a constraint. It is essentially the speed of light. I can't get messages to go any faster than the speed of light. Even quantum networks are restricted to the speed of light. They're instantaneous, but they're not instantaneous. When you start looking at quantum networks, anybody look at quantum networks? Do you know what a quantum network is? So a quantum network is where you actually take entangled particles and you separate them, and you look at one and then you can see what the other one is at the same time. And these are really weird pieces of physics. So for example, there's this thing called the half-mirror test, where they take a photon and a half-solar mirror. They shoot a photon that's at basically a little slit with a half-solar mirror. So it reflects two different paths. So if you do this through a fiber optic cable, it goes down two different paths, and then they aim it back so that it collides. The two halves, they're not really halves, they're both photons. It's kind of, this is why I said it gets very mind-bending. They hit each other at the other end, and you can see an interference pattern that indicates that it did go down both ways. Because you wouldn't end up with the interference pattern if it only went down one or the other. But the moment that you put something in front of one of the two outlets, it doesn't go down the other path. And you're like, what? This is really strange. But that's essentially the basis of quantum networks, is to rely on this kind of entangled particle approach. And they work at a distance. There's no physical connection between the entangled particles. That's why they do this. But they can read the state of the particle. So you can send a message on one end of this, and on the other end, someone else can read it. And the best part is, if anyone else reads it, it's immediately obvious. Yeah, like I said, there's some mind-bending stuff there. And these are the kinds of networks that people will start building for in the future. So I don't know what's going to happen there. But the speed of light is still a hard limit. We can't escape that. So the speed of light in fiber is slower than the speed of light in a vacuum. So I recall it's about 70% or something, but I'm probably wrong. I know that it's not as fast. The speed of light in copper is similar. Of course, mostly in copper, what we're worried about is the speed of electrons, which turns out to be very similar. And the lost property here is that we lose linearizability without coordination. Coordination requires round trips. Round trips mean that we can never do this in less than 1 millisecond. So it's just a physical property. If you want this, the way to escape it is to say, hey, let's just keep replicas close. Which kind of defeats the purpose of geo-replication. Or you look for weakened consistency models. Or you use external things like Spanner's clocks with the commit wait. But that still doesn't eliminate the latency. They didn't get to sub-millisecond. They got to sub-7 millisecond. Or maybe what you do is you mix and match. You use strong consistency when you need that. You use weak consistency when it's okay. Lots of times that things are okay. You're putting things into the shopping cart, we'll be a little lax about that. But when you're actually cashing out in your shopping cart, that's when we need our strong consistency. That's when we update our database. So sometimes the constraints can actually just literally be physical laws. And if you really want a mind-bending experience, go read almost anything out of modern physics. It kind of plays with your head. All right, so impossibility isn't limited to distributed systems, right? This is a model. An AI actually generates text, and you have the model check to see if this text is correct. This is a good example, one that I've been using a lot lately. The checker that does this is the same system that produced the text. How do you know an AI, an LLM is lying to you? You can ask it, right? It'll tell you, sure. How many of you have used an AI? How many of you had one tell you something that you know is not true? But if you ask it if it's true. So last fall, I saw this post on X by this woman in Japan who's an AI researcher, and what she observed was she was asking Grok, of all things, about her own work, and Grok was just making stuff up. And so she pointed out to Grok that it was making stuff up, so it then proceeded to make something else up. So she went through a loop 17 times of these kinds of things. And I looked at that and I said, well, I've seen that pattern myself. And I said, that's kind of interesting. So I built a little experiment, put a blog post about it, because I built a little experiment and I said, I'm going to ask for a summary of a paper that doesn't exist in a time frame that's relatively recent, so it won't be in any of the trained AI models, and see what I get back for responses. And in the end, I swept OpenRouter. At the time there were 333 models. I swept OpenRouter. 290 of them returned actual results as opposed to rate limited errors. The free ones often give you rate limited errors and whatnot. So it's like, okay, great. 290. What do you think the percentage was of them that fabricated a response? Not quite, but it was pretty close. It was 92%. Now, in all fairness, of the 92%, there was a sliver of 29% that actually put a disclaimer into a multi-thousand token response. So, you know how they can kind of gush and go on and on and on, and somewhere in there it said, well, I don't really know, but this is what it probably would be like. And I looked at that and I said, okay, well, that's even worse, because this is kind of like the fine print in one of those contracts that no one reads. Because, I don't know about you, but when I get wall text, I skim it. Not really interested in it. Could you please give me the ELI 5 version of that? So, there you go. A model evaluating its own output is like Paxos trying to guarantee its own liveness. Doesn't even make sense to ask the question. In fact, what I actually ended up finding was that you can look at not information the model expresses, but information that the hardware running the model expresses. It actually has measurements for effectively when it had to stretch to construct an answer. It's very interesting. So it turned out to be a pretty good signal, except in very small text cases. The hardware doesn't show anything when it starts fabricating a citation. It has no problems fabricating citations, and so far, the only way I know of to actually verify them is to go check and see if the citation is fabricated, and odds are, if it's coming from a large language model, it is. So, this kind of impossibility applies in other domains as well, is really the point of that. So here we go, we'll organize a zoo. FLP, we can't tell slow from crashed. CAP, we can't reach the other partition. In the two generals case, we can't confirm delivery of the message. In the Byzantine case, we can't tell honest from liar. So it's always the same kind of problem that leads us here. So here's the thing to think about. You're designing your distributed systems protocol. Someone claims it achieves a strong consistency, always terminates, and tolerates arbitrary asynchrony. I mean, at this point, I hope that you're like little lie detectors going off, going, right, because I just spent an entire term in a class that said that can't possibly be done. Obviously, the fact that I didn't know what he was talking about. How do you know that that claim is false? What questions would you ask? That's a really good one. What would you ask someone? See, if you're trying to convince somebody they're wrong, I will tell you that almost assuredly the least successful route for doing that is going, you're wrong. You want to do it? Ask them questions. Okay, well, what do you do when this happens? Oh, I didn't think about that. There's this dead dude who actually used this technique. And it was so successful that they sentenced him to death. His name was Socrates. So this is what we talked about. And next time we'll actually talk about Spanner. Because we're going to really look at, that's a real world system. This is the way we actually solved it. It is interesting from that perspective. So let's see, right, the paper for Spanner should be up. Go ahead and read it. We're going to talk about georeplication in general, and then I think that's it. Oh, and of course we're 16 days? 16 days from so free state. I think somebody asked in one of the classes which have similar structures. They ask about if they just don't submit any code. It's hard to write a design document against code that you don't submit, but you're welcome to do that, but the code that you rely on has to be frozen as of the code free state. You don't get an extra 2 weeks to work on your code to write a design document. That's the whole point, is that the design is a reflection. It's not intended to be a 2-week extension. Because the benefit here is when you build something that's really good or really bad, you can look back and say, why was it good? Why was it bad? What would I do differently next time? It's the reflection that's really the value. That's the part that I'm most interested in seeing, because that's the skill set you're going to need when you go out there in the real world and people hand you ambiguous tasks and say, here, go solve this problem and tell us what you figure out. And then you come back and you want to be able to show them something that's really snazzy and excellent. And then you can also like have that honest, oh, well, we'll put this in production. You know, I don't think it's quite ready yet, but here's what it needs. That's a good skill set. I mean, how many of you plan on developing software when you're done here? I mean, obviously, the rest of you are just going to be like, you know, stay in the basement and play video games for the rest of your life, and that's fine too. There's nothing wrong with that. You can blame it on AI. All right, thanks, and I'll see you on Tuesday.
I forgot.